This is a lab exercise captured on video on the topic of continuous wave (CW) and Doppler radar operations taken from the Lab 3 of the Dreamcatcher ME1500 University Courseware. We are going to introduce the basic operations and study the working principles of a CW and Doppler radar system. To get the most out of it, you should view the video along with the lab sheet. Please download the lab sheet from this link. You may want to pause this video to read the lab sheet before proceeding with the video streaming. Continuous wave radar, or also known as CW radar, is a type of radar which continuously transmits electromagnetic wave to the target. The radiated signal will be reflected from the target and received by the radar receiver. If the target is moving, then the frequency of the received signal will be slightly different from the frequency of transmitted signal. This is due to Doppler effects. On the other hand, if the target is stationary, then the frequency of the received signal will be identical with the transmitted signal. Hence, a CW radar can only be used to determine the radial velocity of a target, but not the range information. The radial velocity of the target can be calculated by utilizing Doppler effect. Hence, it is able to differentiate between a stationary target and a moving target. Doppler effect is a phenomenon where the center frequency of a transmitted wave is shifted due to the target motion with respect to the source of radiation. The frequency shift is denoted as Doppler frequency, and it can be calculated as 2 times the velocity of the moving object over lambda, the wavelength of the radar carrier frequency. For closing target, which is target approaching the radar system, the wavelength of the reflected signal will be lower than the transmitted signal. For opening target, which is target moving away from the radar system, the wavelength of the reflected signal will be higher than the transmitted signal. In this lab experiment, we are going to measure the Doppler effects by using the Dreamcatcher ME1500 radar training kit, an Agilent spectrum analyzer, and an Agilent digital oscilloscope. The ME1500 training kit consists of a radar hardware kit, microstrip patch antennas, and radar waveform synthesizer software. The radar hardware kit consists of 2 main modules, the radar transceiver module and the radar baseband module, which is located beneath the transceiver module. A PC-based radar waveform synthesizer software is used to configure the radar baseband module for various operations. The radar transceiver module is a super heterodyne system consists of a voltage control oscillator, an up convert mixer, a power amplifier, and a down convert mixer. Next, the radar baseband module is made of an FPGA-based high-speed signal generator and data acquisition unit. The main functions of this module are to produce control signal for the voltage control oscillator, generate the intended baseband radar signals, and to digitize the down-convert reflected signals. The radar waveform synthesizer software will communicate with the radar training kit to generate baseband signal and control the carrier frequency of the radar training kit. The DAC control panel 1 is responsible for generating baseband signal, while DAC control panel 2 is responsible for generating control signal for the voltage control oscillator. The function of ADC panel is to digitize the down-converted analog signal for digital signal processing. Now let's begin with the experiment with source measurement. In this session, we are going to study how to adjust the radar carrier frequency by varying the tuning voltage using radar waveform synthesizer software. First, make the following connection. Connect the DA2 output port to the VTune port. Connect the spectrum analyzer to the VCO port. Lastly, connect the unused ports by using 50 ohms terminator. On the radar waveform synthesizer DAC control panel 2, select DC voltage with tuning voltage set to 0.5 volt. Then switch on DAC2. By varying the tuning voltage, we can control the voltage control oscillator output frequency, hence adjusting the carrier frequency of the radar system. On the spectrum analyzer, adjust the center frequency to 5.3 GHz. with a span of 400 MHz. Set the input attenuation to 10 dB with resolution bandwidth of 100 kHz. On Spectrum Analyzer, observe the frequency and power level of the signal generated by voltage control oscillator and record down the observation. Now, you can observe that there is a signal appearing at 5.174 GHz. By varying the tuning voltage, the frequency of the signal will be shifted accordingly. Increase the tuning voltage by 0.5 each time until 4 volts, then record the observation. From the result, you can see that by increasing the tuning voltage of the voltage control oscillator, the frequency of the output signal will increase from 5.174 GHz to 5.357 GHz. While at the same time, although with increased tuning voltage level, the power level of the output signal remains the same. The sensitivity of the VCO is calculated as 57 MHz per volt. Now plot the graph of the VCO output frequency versus tuning voltage. To obtain desired carrier frequency, you can always refer to the chart and choose the appropriate tuning voltage. From the graph, in order to obtain operating frequency of 5.3 GHz, the tuning voltage shall be set to 2.65 volts. Next, we are going to demonstrate the Doppler effect of moving target by using ME1500 training kit together with an oscilloscope. You might need a friend to help you conduct this experiment. Connect the transmit antenna and receive antenna to the training kit in quasi-static configuration. The transmit antenna will radiate the electromagnetic signal to the target, and the reflected signal will be received by the receive antenna. The down-converted received signal from the IF output port is captured on the oscilloscope. On DAC control panel 2, the tuning voltage is set to 2.56 volts to generate a carrier frequency of 5.3 GHz. Ask a student to stand still at the distance of 100 cm from the radar system and note down the observation as seen on the oscilloscope. From the observation seen on the oscilloscope, it is easy to notice that with stationary target, a constant DC signal is shown on the oscilloscope. This means there is no frequency shift detected for the measurement. At the same distance, ask the student to move towards the training kit and note down the observation as seen on the oscilloscope. It can be observed that the signal appeared on the oscilloscope is fluctuated due to the Doppler frequency shift, which is caused by a moving target, and the sinusoidal wave could be related to the frequency of the target. In previous experiment, we have done the Doppler measurement with the help of a friend. Now, we are going to measure the Doppler effect by using a mini table fan to observe the Doppler effect of a fast-moving target. With identical configuration as previous Doppler measurement experiment, place the mini table fan in front of the radar training kit at a distance of 30 cm. Switch on the mini table fan and adjust its position until maximum amplitude observed on oscilloscope and note down the observation. Now, adjust the distance of the mini table fan to 60 cm from the radar training kit and note down the observation. Now, switch off the table fan and observe the changes of the signal seen on the oscilloscope until the spinning of the table fan comes to a complete standstill. From the observation on oscilloscope, the Doppler frequency is measured at 92.59 Hz when the fan is placed at 30 cm, and the velocity of the moving object is calculated to be 2.62 meter per second. An almost similar result is also obtained when the fan is placed at the distance of 60 cm. The Doppler frequency is measured to be 91.74 Hz, and the velocity of the moving object is calculated as 2.6 meters per second. These results prove that the Doppler radar is able to extract velocity information of the target regardless of the distance of the target. Also, it can be noticed that the amplitude of Doppler signal will be affected by the range of the target due to signal propagation loss. The longer the range, the weaker the amplitude. We have done the CW and Doppler radar experiment through ME1500 radar training kit. Now, let's simulate the CW and Doppler radar by using Agilent System View software. The simulation begins by creating a schematic to represent the CW radar signal generating using VCO. First, Construct a VCO with constant generator which represent the tuning voltage to control the VCO output frequency. Then, input a data sync with spectrum analyzer to observe the output frequency of the VCO. Double-click on Design Analysis to open the Data Flow Analysis dialog box. Set the system sample rate to 20,000 MHz with frequency resolution of 100 kHz. This is to ensure the sampling rate is sufficient to simulate a 5.3 GHz signal with resolution of 100 kHz. In the schematic design window, double-click on the VCO model to open the VCO Properties dialog box. You can always click the Model Help button to read the description of the model. Now, by referring to earlier measurement result obtained in VCO source measurement, set the sample interval to 1/sample rate. In this case, the sample rate is equal to 20,000 MHz. And the fundamental frequency is set to 5.12 GHz with sensitivity set to 57 MHz per volt. Then click OK. Next, set the VCO input, which is the constant generator, to tunable and use a slider to tune the VCO. To link the slider with the constant generator, double-click on the slider and choose the variable as C1. Set the maximum of the slider to 5. Once the schematic is constructed, run the analysis to plot the output spectrum of the VCO at different input level. To show the tuning window of the constant generator, click View and select Tune. Now you can see the tune window appears at the bottom left of the window. To enable the auto recalculation, click on Design Analysis. To plot the output of the spectrum, double-click on Design Data. Right-click on S2 Power and select New Graph. Adjust the X-axis and Y-axis scale before you click OK. Now, you can observe that with the tuning voltage set to 0, the VCO output frequency is observed to be 5.12 GHz. Adjust the constant generator value in order to achieve VCO output frequency of 5.3 GHz. As you can see, the VCO output frequency increased as we increase the tuning voltage. You can always change the step size of the tuning voltage to achieve better accuracy of VCO output frequency. Now, you can observe with constant generator value of 3.2, the VCO output frequency appears at 5.3 GHz. We have seen the simulation of CW radar signal generation using VCO, and now we are going to simulate moving target detection using Doppler radar. Similarly, the simulation begins by constructing the schematic of the Doppler radar. First, create a VCO to represent the Doppler radar signal source and input a radar target from radar library. Then, input a mixer which acts as a down converter and link it to data sync with spectrum analyzer. In Data Flow Analysis dialog box, set the system sample rate to 1 MHz and the frequency resolution to 2 Hz. Next, adjust the frequency of the oscillator in the schematic to 5.3 GHz. Notice that the VCO model in previous simulation has been replaced by an RF oscillator model. This is because the carrier frequency of the oscillator is a prefixed value and it does not rely on the system sample rate. Hence, we can use a lower sample rate and focus only on the baseband simulation and analysis. The radar target in the schematic represents a moving target with variable velocity so that we can simulate its Doppler effect. In the radar target properties dialog box, set the target's RF frequency response to 5.3 GHz and the target distance of 50 meters. The time step is adjusted to 1 over sample rate and the duration time is set to stop time. The velocity of the target is set to tunable and use a slider to tune the velocity. Double-click on the slider and select the variable as radar target. Set the minimum of the slider to -5 with maximum as 5. Then, enable auto recalculation and adjust the radar target velocity step size to 0.5. Run the analysis and plot the Doppler frequency shift of the radar at various velocities ranging from -5 to 5 meters per second. Before you plot the graph, adjust the x-axis scale from 0 to 300 Hz. You can click on the signal to add a marker. Right-click on the marker and choose Peak. Slowly adjust the velocity of the target until you obtain a Doppler frequency similar with the measured Doppler frequency obtained from Doppler measurement of the fast-moving target. You can now compare the simulated results with the measurement results obtained in Doppler measurement of fast-moving target. Through the experiment, we understand that Doppler radar operates by using the Doppler effects of moving object to identify the speed of the object. We have also measured and simulated the Doppler effect of slow-moving target and fast-moving target, as well as the control of the VCO output frequency. Doppler radar could be utilized in military defenses to identify the speed of incoming threat such as a missile or fighter jet. The Doppler radar can also be used as speed trap to identify vehicle speed.